Great, and I'll stop sharing and Anindya, take it away.
Okay. Okay, so thank you organizers for giving me the chance and 1 minute. Can you see?
Yeah.
Oh, yeah, okay. Okay, so before I start, I'm going to talk about Leafwise Quasigeodesic foliation in dimension 3. Whatever I'm saying mostly is in dimension 3 with funnel and non-funnel leaves. So I just want to say that I will not use any type of technical term. So I am trying to be the all the definitions I'm using, or I will mention all of them are kind of just a vague idea. I will not use any technical definition. So yeah, and if you have any question, you can stop me anywhere. I don't mind at all. So let's see. So my talk is, I mean, it's mostly about what I'm going to talk about. It is kind of some geometric property of foliation in a particular situation. So let's start with the definition of foliation. What is a foliation? So I do not know what is this. Okay, so what is a foliation? So foliation is kind of filling up a higher dimensional manifold with lower dimensional immersed submanifold. Just think about filling the Rn, a higher dimensional Rn, with copies of smaller dimensional Rm, right? And in a foliation of a manifold, we just kind of copy the same structure. Like when we define manifold, we just copy the local structure of some Euclidean space. It is the same idea. So you have some higher dimensional Rm, you are filling it with lower dimensional Rms, and you are just copying those local structures. Okay, these immersed submanifolds are called leaves of the foliation, and here I have two very basic example of foliation. So first of all, if I fill R2 with lines, that is the one foliation. And the second one, this one here, it is called the rip foliation, and it is kind of a bad guy in math. So uh, if in the study of foliation, if you have rip foliation in some situation, you are restricted to have a lot of properties. So we do not want them to be in our manifold. So yeah, I mean, they are good and bad. Okay. So the previous picture was, it is a reap component or reap foliation on kind of the whole plane, but mostly, I mean, when we talk about them in a manifold, we consider reap foliation over an annulus, or sometimes, I mean, we can have them on torus. Sometimes we can have them on solid torus. That is a, I mean, when it is in the solid torus, it is in a kind of three-dimensional manifold, and the foliation is by the plane. Okay, so it's a two-dimensional foliation of a three manifold. Okay, so these are some pictures of rip component of annulus and rip foliation on torus. We are going to use them in our talk today. Just a note that if I have a C1 foliation, then that always defines a non-zero vector field. Like you can just differentiate the foliation structure and that will give you a vector field. But from the Poincaré-Hopf theorem, we know that, so if we have a singularity of a vector field, then uh, you can apply the Poincaré-Hopf theorem, and which says that the sum of the singularities and with sign that should be equal to the Euler characteristic, right? But if you do not have a singularity, then it should, the sum in one side should be zero. So the Euler characteristic of the manifold you are talking about should be zero. But torus is the only such manifold, closed manifold. So we can have a non-singular foliation only on the torus in dimension 2. Okay. Okay, so now I am going to the kind of main situation we are going to talk about. That is, it's a situation called subfoliation and superfoliation. It is like just like subset and superset. So what I have a manifold. I have a higher dimensional foliation. So suppose I have a m dimensional foliation and I have a lower dimensional foliation on the same manifold that is of dimension n, but the property is all the leaves of the bigger foliation is also foliated by the smaller foliation. Like you can foliate the R3 using the vertical planes, right? And that is a two foliation. Again, you can consider the one foliation of the R3 using the vertical lines. And all the vertical planes are also foliated by vertical lines, right? So this is the situation we are talking about. On the same manifold, we have two foliations. Leaves of one foliation is subfoliated by the other one. Okay, the bigger one will be called superfoliation, and the smaller one is called subfoliation. Okay, so this is the kind of picture of a superfoliation and subfoliation. This is a very common situation we have in the in our studies. So yeah, we are going to talk about a special, we'll consider a little more geometric structure with subfoliation and superfoliation. Okay. Next, if we have a foliation on a manifold, they actually behave nicely with the covers. So if I take the universal cover, you will get uh, a foliation in the universal cover will actually project down to the lower manifold, the actual manifold, and all the leaves of the foliation in the universal cover are also universal covers of the leaves in the lower manifold. Okay, so everything actually behave nicely with universal cover. Okay, now we are taking our first assumption, that is, suppose we are talking about a foliation, a two foliation, such that that all are Gromov-hyperbolic when they are lifted to the universal cover. Okay, so if you do not know what Gromov-hyperbolic is, you can just think about hyperbolic disk. Okay, it is a kind of same thing. Okay, so for today, I think that definition is sufficient. Just think about hyperbolic disk. So I have a two foliation on a three manifold such that if I take it to the universal cover, all the leaves of the foliation in the universal cover are made of hyperbolic disk. Okay. Next, I have a subfoliation and superfoliation situation. So I have taken a three manifold. I have taken a two foliation such that all the leaves are Gromov-hyperbolic. And then I am taking the one foliation which also subfoliate the two foliation. But my next assumption is all the leaves of the one foliation are quasi-geodesic inside the leaves of the two-dimensional foliations, and everything is happening inside the universal cover. Okay, now what is quasi-geodesic? Quasi-geodesic is, geometrically they are boundedly distorted from an actual geodesic. So kind of a perturbation of a geodesic. So we call it large scale geometry. So maybe, you can think like that. If you look from a very far, you cannot differentiate which one is a quasi geodesic and which one is a geodesic. Okay, so something like that. So quasi-geodesic is a kind of boundedly distorted curve from a geodesic. That is the definition of a quasi-geodesic. So from my assumption, the leaves of the one foliation, they are quasi-geodesic inside the leaves of the two foliation, and it is with respect to the induced metric. Okay. Now we have a two foliation such that all the leaves are Gromov-hyperbolic. We have a one foliation such that all the leaves of the one foliation are quasi-geodesic. We will say leafwise quasi-geodesic because we are thinking inside the leaf of the two foliation. And now, because the leaves of the two foliation, they are Gromov-hyperbolic, we can talk about their Gromov boundary, right? And the leaves of the one-dimensional foliation, they are quasi-geodesic, so they will define limit points on the Gromov boundary. Okay, so that is our situation. So before we go further, just bigger idea, but I'm just describing it in one sentence. It is kind of collection of equivalence classes of asymptotic directions of semi-infinite geodesics. So maybe you can see here, this is the uh, hyperbolic disk, and these blue lines, they are actual geodesics. So if I consider this geodesic here and that geodesic here, both of them are kind of asymptotic, and this asymptotic direction defines a point on the boundary. Okay, so if I take the collection of all such boundary points, then I get the perfect circle, and we call it a circle at infinity. Okay, and the green curve here, that is an example of a quasi-geodesic. It is actually a semi-infinite quasi-geodesic. It is only going to infinity in one direction, not in the both direction. But yeah, I mean, even if quasi-geodesics are not actual geodesic, but they also define limit points on the ideal boundary. Okay, so in our situation, we have a two foliation subfoliated by a one foliation, which are leafwise quasi-geodesics, and the two foliation leaves are Gromov-hyperbolic. And we are talking about the boundary of the Gromov-hyperbolic leaves. Okay, now we are ready to define what a funnel leaf is. So take a leaf from the two foliation. So everything I'm talking about is inside the universal cover, and it is a hyperbolic disk like this one. And I know all the one-dimensional leaves are quasi-geodesic. I will call that the leaf L is a funnel leaf if all the quasi-geodesics shares a common boundary point. So this is the situation I have. I mean, all the quasi-geodesics, they are kind of emitting from one particular point. Okay. And this common point is called the funnel point, and this type of leaves are called funnel leaves. So like here, this geodesic, this is an actual geodesic, and that one, these two doesn't share any common boundary point, right? So this is not a funnel leaf. Okay, is there any question so far? Any question? Okay.
Can I ask something?
Yeah.
So if you have two leaves of the one-dimensional foliation and the leaves cross, sorry, here I'm. If you have two leaves of the one-dimensional foliation and the leaves cross, does that happen?
How should I?
Or I guess the leaves shouldn't cross. So does that does that imply that the geodesics never cross?
Yeah. I have not. So I could not understand your question properly. Actually, can you please repeat it?
So you have this leaf of F, and then you have the leaves of G inside, and then each leaf of G is close to a geodesic. And I guess my question is, do the geodesics form a foliation? Are they can they cross each other, or can anything like that happen?
I have never thought about that situation, but probably in this situation, the leaves, the geodesic doesn't cross. Like if I have this type of nice structure, that is the situation what we have for the Anosov flows, right? The unstable or stable, but probably that doesn't happen, but I'm not sure. I never thought about that. Yeah.
All right.
Okay, and F is called to satisfy the funnel property with respect to G if all the leaves of the two-dimensional foliation are funneled with respect to G. Okay, so we have the situations, and what I have here is I am kind of seeing there are some situation where Leafwise Quasigeodesic property is, when I have a Leafwise Quasigeodesic property, I am also having the funnel property. Okay, so now that is the question which arises very naturally, that whether Leafwise Quasigeodesic property alone can define the funnel property. Okay, so we are going to answer the question whether the funnel property is a consequence of the Leafwise Quasigeodesic property or not. I will give another example why this question is important. But before that, I need to define what an Anosov flow is. Okay, but in this talk, we are going to answer this question negatively by constructing a counter example. Okay, so now I'm going to describe the motivating example. That is we have to define the Anosov flow. So what is the Anosov flow? So first of all, flow is a group action of time, that is the real line over a manifold. So so suppose you have a flow on a manifold, we call it Anosov. So probably I should consider C1 here. I didn't mention that. Yeah, so when I'm saying Anosov flow in this definition, I'm assuming at least C1. Okay, so a flow is called Anosov if its tangent bundle is S, that stands for stable, EC, that stands for center, and EU, that stands for unstable, and such that the center bundle, that is actually the bundle which is generated by the vector field in the direction of the flow, the unstable bundle EU, that is the uniformly expanded bundle, that is if I flow further and further, and if I take a vector from the tangent bundle EU, then norm of that kind of increase exponentially. So there is a factor c times lambda to the power t such that this happen. Okay, and the opposite happen for the other bundle, the stable bundle, that is it is uniformly contracted, that is the norm of d phi t of v that can kind of compress exponentially if I go further and further in the positive direction of time. Okay, so in one direction I am expanding, in other direction I am contracting, and the third direction that is kind of sandwiched between these two. Okay, so this is what we called an Anosov flow. Now the interesting part is there are a lot of kind of associated foliation with Anosov flows. So first of all, if we are talking about a flow, the flow lines defines a foliation, and that is a one-dimensional foliation, right? But with the Anosov flows, sometimes we have two more foliation. Okay, so for Anosov flows, we always have these two foliation. They are called the weak stable foliations and weak unstable foliation. So both of them are two-dimensional foliation. So what is a weak stable foliation? So weak stable foliations are kind of the leaves where that compressing is happening. So it is a two-dimensional leaf such that all of them are kind of saturated by the flow lines. So on a leaf, on a quick stable leaf, if you kind of move along two different flow lines, then the distance between the points that, we describe it like phi tx and phi ty, that actually is kind of going to closer and closer to 0. So both of, I mean, all the flow lines are kind of asymptotic in the forward direction. Maybe that is a better description. And for the weak unstable foliation, what happened is all the flow lines on a weak unstable leaf, they are kind of diverging with respect to time. Okay, both of them are two-dimensional foliation, and both of them are saturated by flow lines. So that is a classical subfoliation superfoliation situation. So these weak stable foliation and weak unstable foliation, they are superfoliation, and the flow lines, they form a subfoliation. Okay. Now here is the interesting part. Okay, so I should mention the name of Anosov probably, because this result is due to her, due to Anosov, that Anosov flows always have these foliations. Okay. Now suppose we have a Anosov flow on a 3 manifold, then there are few properties we have that, I mean, then Anosov flows actually have the properties we are actually talking about. That is, if we lift the leaves inside the universal cover, then the leaves are hyperbolic. Okay, and the flow lines, they are leafwise quasigeodesic inside the leaves when we lift them in the universal cover. Okay, so these two are our basic assumptions which we had in our definition, and Anosov flows are the examples. Okay, and the most interesting part is Anosov flows gives us funnel leaves. The weak stable leaves and weak unstable leaves, both of them are kind of funnel with respect to flow lines, but the difference is in the weak unstable leaves, I mean, these lines are all flow lines, that is, they are defining the one foliation, and in the weak unstable leaf, if I go positive in the, I mean, if I go towards the positive infinity, all the flow lines, they kind of diverge, and their common limit point is in the backward direction. And in the weak stable leaf, if I go in the forward direction, all of them kind of converge, and this is the common limit point, the forward limit point. Okay, and all rays. Okay, so this is a result of Finlay, and yeah. Okay, so that is actually the definition. Sorry, that is the example, motivating example behind funnel leaves. And now we are going to describe a little bit why we answered the question we are talking about today. So suppose we have a foliation, which, I mean, I have a one-dimensional foliation which is given by a topological flow. And suppose we have a two foliation which is subfoliated by that one foliation. Okay, and we have the properties that G is Leafwise Quasigeodesic on F, and F and G, they satisfy the funnel property. Then it is proven in a recent paper that in this situation, if we have the funnel property, that means the flow in the question is, which we called expansive, and which can be also proven to be, I mean, in that sense, that topological, I mean, what we call topological Anosov. Okay, so that is actually a very strong dynamical property. Okay, so if leafwise quasi-geodesic property actually imply the funnel property, then what we have is a very geometric property imply a very strong dynamical property that the flow in the question is Anosov. Okay, so that's why it is important to answer this question. In fact, I mean, there is some connection with this question with partial hyperbolic dynamics. That is a kind of new area of research. Okay, but yeah, so we are going to answer this question negatively, and we are going to construct a counter example. So what do we need to do? Okay, any questions so far? Any question? Okay, so what we need to do? We need to construct a counter example. So first of all, we need to construct a suitable manifold. That is a manifold M. That's a 3 manifold we are going to construct. Then we need to construct the subfoliation and superfoliation, and we will use some type of Anosov flow to do that. And then we also have to prove that the leaves are hyperbolic. I mean, the leaves of the two foliation is hyperbolic when they are taken to the Leafwise Quasigeodesic, but the leaves of F may be, I mean, there are some leaves of F which are funnel, and there are some leaves of F which are non-funnel. Okay, then it will prove that the Leafwise Quasigeodesic property alone cannot imply the funnel property. Okay, so let's start with defining the manifold. So this is actually, I mean, we are starting with a classical example in the field of dynamical system. It's a famous example by Franks and Williams. So using this example, they actually prove that there exists non-transitive Anosov flow. So by non-transitive, I mean it is a flow such that there does not exist any dense orbit. Okay, so I am starting with torus, two torus, and I am taking a hyperbolic map. That is, just take a hyperbolic metric, maybe 2, 1, 1, 1, the most famous example probably on the torus. So what is the geometric property of this map? It is expanding in one direction, in one eigenvalue direction, and it is contracting in the other eigenvector direction. Okay, so it's expanding in one direction, contracting in the other direction, and the center 0, 0, that is a fixed point. We call it hyperbolic fixed point. Okay, next we are blowing up the unstable direction of the fixed point. Okay, like this. So after the blow up, we actually have 3 fixed point. This is one fixed point. That is another fixed point. Both of these two are what we call hyperbolic fixed point, and I have a fixed point at the center. Okay, this is actually called DA construction. That is starting with a hyperbolic map and then transforming it so that we have a source point. See, I mean, after the blow up, the origin that becomes a source. So we have a map on the torus such that we have a source point, and this blow up leaves, I mean these two, this curvy one, these two becomes kind of attractor. Okay, so in this situation we have a I have a point source and a one-dimensional attractor. Okay, so next what I'm going to do is I'm going to consider the mapping torus of the blow up map. I'm going to call the blow up map A and take the mapping torus of it. Okay, the mapping torus is a 3 manifold and it is equipped with a very natural flow. That is, just take the label T. Okay, so that is my underlying manifold. Okay, so not so far yet. I'm going to do little more. So yeah, we have already seen that that was the map. After the blow up, it had an attractor and it had a point source. So after we take the mapping torus, the one-dimensional attractor that becomes a two-dimensional attractor now, right? So just take the map and the fixed point, the point at the center, that gives me a circle in the mapping torus. Okay, so I am showing it in the universal cover, so I am representing it with a straight line. Okay, so the green line, that is actually a circular repeller kind of thing. Okay, in the next step, what I am going to do is I am going to take a neighborhood of the circle and cut it out. Okay, so I have a 3 manifold with a circle inside it, which is a repelling circle, and I am kind of cutting out the neighborhood, a torus neighborhood of the circle. Okay, so that is my manifold now. I call it M1, that is take the manifold and cut out a neighborhood of the repelling circle. And this is a manifold with boundary. The boundary is a torus. Okay, so just to note that we had a natural flow on the main manifold M, but even we cut out the torus neighborhood of the repeller, we still have the flow on the rest of the manifold, and the flow lines are going inside of the through the boundary, transversally intersecting it. Okay, and the flow restricted on the piece M1 still have the attractor inside it. Okay, now there is something called the weak stable and weak unstable foliation of the attractor, which is kind of defined like, so we actually can define this type of weak stable and unstable sets for any hyperbolic set, and the attractor is what we call a hyperbolic set, that is, it is expanding in one direction and compressing in another direction. So in kind of easy word, the weak stable leaves are made of the leaves such that if I take a point on the attractor, then a leaf is kind of collection of all the points which are going closer and closer with respect to forward direction of time. Okay, so it is kind of same as the weak stable leaf of the Anosov flows, the same kind of geometric behavior. Okay, we can consider weak stable leaves for attractors or repellers or this type of dynamical sets, which we called hyperbolic sets. Okay, and these weak stable leaves, this is actually a two-dimensional foliation, and this two-dimensional foliation will intersect the boundary torus, right? And the intersection is a interesting object. It is it will define a one foliation on the boundary torus, and it have two rib components like this. Okay, so this blue one is the boundary torus which we had in the previous figure. So this is the torus, and now suppose the weak stable foliation is kind of the vertical planes, and they kind of intersect the torus in two rib components. Okay, so that is my piece M1 with the equipped flow, which is going inside, and we have attractor. Take another copy of M1, call it M2, but this time take the reverse flow, the flow in the reverse direction. So the repeller inside the M2, sorry, the attractor inside the M1 will now become a repeller. Okay, and then all the flow lines are kind of going transversally outside of the through the boundary. Okay, and now you can kind of patch them up. Just as we defined the weak stable foliation for the attractor, we can define the weak unstable foliation for the repeller, and it will also intersect the boundary in the same manner, and that was the intersection of the boundary of M1 in a one foliation with two deep component. Similarly, the unstable foliation will also intersect the boundary with two deep components. Okay, and next what we are going to do is we are going to attach these two pieces along this boundary. Both of them are torus with the same foliation, but we will attach them with kind of a rotation, so that these two foliation in the previous figure, they becomes kind of transversal to each other. Okay, so that is a crucial point. We will use that. I have not mentioned it probably in the letter of the talk, but that is a important thing. Okay, that taking these two foliations transfers to each other. And Then we attach these two pieces and we get a 3 manifold, and the flows on the two pieces, they nicely attach to each other, and we have a flow on the whole manifold which kind of extend both of the, restricted flow on the pieces. So we have a flow on the whole manifold, and this is a classical result of Franks and Williams, that the flow is Anosov. It is a non-transitive Anosov flow which with a attractor inside the piece M1, and it has a repeller inside the piece M2. Okay, and the flow lines, obviously they will define a foliation, and that foliation is the one-dimensional foliation we are going to use. Okay, so the foliation by the flow lines of this Anosov flow on this constructed 3 manifold is going to be our one foliation. Okay, so we got our one foliation. Now we need to find out a two foliation. So what we're going to do is, so first consider a one foliation on the boundary torus, which is transverse to each of the intersection of weak stable and weak unstable. So this was the foliation structure I already had on the boundary torus. I am going to consider a third foliation, the foliation in the blue lines, which is transverse to both of them. Okay, so still now that is a foliation only on the torus, the boundary torus. Next, what I am going to do is I am going to take the flow saturation of this one foliation, which I just mentioned. I will denote that with F, and I am going to take the flow saturation of that foliation on the torus. That is just flow the foliation F. If L is a leaf, then consider the image of the leaf L over the whole flow. Okay, that will be something that will be a two-dimensional object. And if I take the collection of all of them, that will define a two foliation, not on the whole manifold, but on the flow saturation of the torus. Right? So if I take the boundary torus, the boundary of M1 and M2, the common boundary, and if I kind of move it using the flow, then I will have a open set inside the whole manifold, and still now I have defined the foliation only on that open set. Okay, now I can actually break my whole manifold into three different disjoint parts. This is the open set we just talked about. The rest of the part will be the union of the attractor and the repeller. This is not immediate to see, but I'm not going to describe why that is true. Just believe me. Okay. So yeah. So still now I have defined the foliation only on the open set. I still have to define, then it will be a foliation on the whole manifold, right? Now on the attractor and the repeller, I am going to use the weak stable and weak unstable foliation of the flow. So the attractors of a Anosov flow is actually saturated by the weak unstable foliation of the Anosov flow, and similarly the repellers are saturated by the weak stable foliations of the flow. Okay, so I am extending my foliation F, which we defined on the flow saturation of the torus, on the attractor by defining that the foliation F on the attractor is the restriction of the weak unstable foliation on the attractor, which we already had, and on the repeller we are taking the restriction of the weak stable foliation, which we already had. Okay, so that defines a foliation on the whole manifold. Okay, so here is a subtle point that it is not always immediate why that defines a foliation, but the proof we had is kind of technical, so I am not going into that. But yeah, so that's a two foliation on the whole manifold. And we have a two foliation which is subfoliated by the flow lines. So that is a superfoliation, subfoliation situation. Okay, but that is just the foliation. Now, what yet I need to prove? I need to show that each leaf of the foliation F, they are Gromov-hyperbolic when lifted to the universal cover. Then I need to show that each leaf, each flow lines are leafwise quasigeodesic on the leaves of the two foliation. And the most important part, this two foliation F should have both funnel and non-funnel leaf. That is the property I am going to show. That is the main property, right? Okay. Yeah.
If you can wrap up in about 5 minutes, that would be great.
Yeah. I think, yeah, I'll be done with it.
Okay, great.
Yeah. Okay. So just talk about what we already have. So on the attractor and on the repeller, on the attractor, I have the weak unstable leaves, and on the repeller, we have weak stable leaves. So that is a result of Fenley that on weak, these two leaves are funnel with respect to flow lines. Okay. So inside the leaves, inside the attractor and the repeller, we already have funnel leaves. That's the result of Fenley, and the leaves look like this. So the red one is the weak unstable, the green one is the weak stable, and these lines are the flow lines. Okay, so we already have the funnel leaves, but we still have to find out some non-funnel leaves. So let's see. Okay, so that is another important property we need to use sometimes. So that is, if I take a flow line which is not contained in the attractor or the repeller, then in the forward direction, if I take the forward ray, then there exists a unique flow line inside the attractor such that the forward ray is asymptotic ray. I can find a unique ray inside the repeller which is asymptotic to it. Okay, so that's a classical result in dynamical system, and we had to use that. Okay, so now we have to prove 3 points. First of all, why the leaves are hyperbolic, the two-dimensional leaves are hyperbolic. Secondly, why the leaves of the one foliation are leafwise quasigeodesic, and third, what are the non-funnel leaves. So the hyperbolicity is kind of, I am not describing a lot about that because to define it, I have to use some invariant measure kind of thing. I'm not going to define that. But yeah, so the main point is, if I do not have a measure, if we do not have a holonomy invariant measure, that kind of imply that all the leaves of the foliation are Gromov-hyperbolic. That's a result of Candle, and that is what we have used. So because some of the leaves are and leaves of the Anosov flows, we cannot have that. Okay, I'm not going into the details. Okay, now let me talk about the important properties of the flow lines. So we have already discussed that the flow lines in the leaves of the weak stable and the weak unstable are leafwise quasigeodesic, and the flow rays are kind of asymptotic in the forward direction and in the backward direction to flow lines inside the weak stable and weak unstable. So we have actual leafwise quasigeodesic leaves, and we have asymptotic rays to them. Okay, that proves the asymptotic rays are also quasigeodesics inside their leaves. Okay, now because the flow rays are quasigeodesic, they will define Gromov points on the Gromov boundary. Okay, so, but still now we have only the rays. We not talking about the flow lines. We have to prove the result for the flow lines. But the flow rays, they actually satisfy three very beautiful property. First of all, if I take a point and if I take the forward ray and the backward ray, this, the forward ideal point and the backward ideal point on the boundary, they are not the same. Okay. Secondly, if I take two different points, I have to mention that, such that their flow lines are not also the same, then their forward ideal point and the backward ideal point are not the same. So this is actually the property which proves that the leaves we are talking about cannot be funnel, because two different flow lines does not have the common forward or common backward limit points. Okay. And the last one, that is the most important property of this setup, is that these maps, the positive limit point and negative limit points, these maps are kind of continuous on the topological space of Gromov boundaries. Okay, so using the previous properties, we can prove two further properties of the flow lines. So the properties in the last slide was, the floor lines are quasi-geodesic. So these are the two property which kind of imply the Leafwise quasi-geodesicness of the flow lines. So the first of all, if I take a flow line and if I connect the geodesic, which connecting the forward limit point and the backward limit point, then there is a universal D such that the flow lines is contained in the D neighborhood of the actual geodesic. Okay, so that was, that is a property of quasi-geodesic, but we are proving it in the backward, in the opposite direction. Okay, and the secondly, along the flow line, if we move along a, for a finite length, then in the projection on the copying geodesic, we also have to move a finite distance. Okay, so it cannot happen that along the flow line we are moving a long distance, but in the geodesic sense we are moving a very short distance. Okay, so these two properties together prove that the flow lines are leafwise quasi-geodesic on the leaves of the two foliation. Okay, so we are actually done. We have proved that the leaves of the two foliation are Gromov-hyperbolic. We have proved the flow lines are leafwise quasi-geodesic on them. And we have proved that the leaves of the two foliation outside the attractor or the repeller cannot be funnel, because if we have two different flow lines, their forward and backward limit points are not same. Okay, so inside the repeller and the attractor, we have funnel leaves, but outside them, all leaves are non-funnel. So that's answered the question. That is what we are looking for. Okay, so that's actually ends the talk, and thank you so much. So any question?
Thank you so much. I think we have time for one question maybe, and then we'll take a bit of a break. And if there are any more questions, we can discuss them during the break as well. So are there any immediate questions?
So this foliation is tangent at points to the weak stable and the weak unstable foliation, like they share some leaves.
No, so this foliation is actually everywhere transfers to the weak stable and weak unstable.
It's transverse,
yeah,
everywhere, so, like even on the attractor and repeller.
Yeah, it's actually it's transfers everywhere. But if I am going forward, it is going more and more asymptotic towards the weak unstable, and if I go for backward, it's getting more and more asymptotic to the weak stable.
But then you have to include the leaves. You have to include the weak stable unstable leaves in the attractor, or
yeah. So what I'm saying is, outside the attractor and the repeller, it is transfers.
Okay.
Yeah.
Great. Let's thank Anindya again. And thank you very much, especially joining so early in your time zone. So we might take a 10-minute break, if that's okay with everyone. So come back at about 6 past, 7 past 11, and then Ed can start his talk then.